Hello, everyone. Great to have everyone here, and nice to see everyone today. And welcome to this year's QHack 2024. It's going to be a great... Sorry? Louder? Can we have it a bit louder? Great. How is that? Is that better? Louder? Okay. How was that? Louder? Well, welcome everyone to QHack 2024. It's a pleasure to be here and to welcome you all, and hopefully we can get a chance to chat while you're here. QHack now is into its 5th year, which is quite remarkable. This is actually the first time I think they've let me do the welcoming, so it's probably the highlight of the 5 years, my guess. So welcome, and it's also, I believe, the first time since 2019 we've had an in-person event for QHack. So it's really great to see people here in person. We've also got a lot of people online. And I was looking at the stats the other day. We've had, including this year, we've had over 10,000 participants. A lot online. I think COVID made those numbers go up, and we've continued that to this day. But it's a really exciting event to have, and really shows you when we started QHack 5 years ago, it was really in its infancy, quantum software in general, the industry in general. And so you can tell by our wonderful sponsors that we have here that it's really representative of the industry in general. So first off, thanks to our sponsors as well. And hopefully you're going to have a really great time here. I originally from Australia, and so I've come to Toronto a few years ago now. And Xanadu was built here in Toronto to our main headquarters. And it's a really lovely city, a lot of great people here, and it's a wonderful town to really build a great company here. We'll have a lot of people around on hand here to help you and answer any questions, and I'm always available as well. And that's really it for me. Just have a wonderful time, and thank you for coming and attending. Thank you.
Right. Anybody who doesn't want to be in the picture, you can hide your face. I don't know, hide under the chair in front of you. But hopefully everybody will want to be, and we're happy to share this.
Where do you want me to sit? I look a little awkward.
You can.
I look like you should be in that.
Yeah, you can sit there, first row. Yeah. Awesome. Now everybody this is going to go on social media, on the Penny Lane social media. So we want all of your smiley faces, excited. Yes, I see some good attitude over there. Awesome. Perfect. Our marketing person is going to be happy. All right, so thank you, Christian. I am shorter than you. I'm going to do like this. You can hear me well? Awesome, perfect. So thank you, everybody, for being here. This is going to be an amazing day. We're packed with events. We have talks, workshops, extended reality artworks, a ton of stuff going on. So I'm glad that everybody's here. If you have any questions, the people with the, eggplant-colored shirt, I think this is the right color. Our designer will be able, yes, I got the right color. The eggplant-colored shirts are the ones who, they say staff in the back. So we'll be able to help. We're going to start with a keynote from our very own Nathan Killoran. So he's an expert in quantum machine learning. He's one of the founders of the field, and we're very happy to have him at Xanadu. So thank you, Christian, for having Nathan in the team, for finding Nathan, make him part of the team. I personally, I'm Catalina. I didn't introduce myself, sorry. I'm Quantum Community Manager, helping organize this event together with Isaac here, who's on our stream. So hello to everybody who's watching on the stream, probably here. We're going to have some streamed talks. So a lot of the talks today are going to be streamed so that everywhere in the world you can enjoy them. We're going to start with our keynote by Nathan at 10 a.m. So we have a little bit of time before that. We're going to have a talk by Katharine Hyatt, so over there here, joining us from AWS. The talk is called Hill Climbing and Valley Crossing. So both of these talks, the keynote by Nathan, better than classical, question mark, we're going to see. those are going to be happening here. So you're going to be seeing some schedules like printed around. They're going to be at tables around. If they say kitchen, this is the kitchen. Because if you look behind you, there's a kitchen, right? So this is the kitchen. There's going to be another set of talks and workshops happening in something called Olivia. So if you're observant, you're going to see that the meeting rooms have a ton of different names, and the one right behind the kitchen, like on the other end of the floor, is called Olivia. So you're going to see some things happening here in the kitchen, some things happening in Olivia, and something happening almost everywhere else. So definitely take a look around. After this intro, we're going to have a little bit of time for you to look around, see what's happening, etc. We are going to have a sign-up sheet for the extended reality artwork. The person hadn't arrived by 9:30, so hopefully she's going to be here now, and we can start with the sign-up sheet. The goal for today and for tomorrow is that you really make the most of this experience. Talk to everybody who's around you, look right and left of where you're sitting, and hopefully by the end of tomorrow, you're going to have their contact. Maybe even you're going to meet them in the future. You never know how much these kind of events can be important for your career. If you're interested in quantum, maybe you're a student, maybe you're already in the field, you have no idea who you'll meet, so definitely take the moment to enjoy, to meet other people. And we're going to have a hackathon, an in-person hackathon. So for everybody who's looking for this exciting coding or creating something experience, we're going to reveal the details at 11 a.m. So definitely attend the workshop if you want in Olivia. If you're interested in having this hackathon with teammates, etc., you can make teams of 4. We're going to reveal the details at 11 a.m. Now, after our talks by Nathan and Katharine here, in parallel, other things are going to happen. So you're going to, for the people on the stream, it's easy. You know where to be. For the people on site, you'll have to make a choice. You'll have parallel things happening, so you'll have to choose where you want to be. So we're going to have a talk, a non-stream talk on photonic quantum computing by myself. And at the same time, we're going to have a talk on how to contribute to Penny Lane in Olivia. So that's more or less how it's going to work today. You're going to have things happening in parallel, and you're going to have to choose what you want to do. For the people in person here, we're also going to have lunch. So lunch is going to be provided on this area. It's called the software area because almost everybody who works on this floor works on this side. You are going to see some desks on the very opposite side of the floor. So Xanadu is located on 2 floors. We're located on the 24th floor of this building. And you're going to see that on the opposite side, we're going to have other desks that are occupied, so people working there. So the recommendation for people who are in person on site, you can use any desk as long as it doesn't have a monitor. Desks that have a monitor are occupied. Desks that don't have a monitor, you can use them. So if you want to work in your hackathon project and you want to use any desk, use it as long as it doesn't have a monitor. So yeah, people working here will appreciate it. All right, there's going to be snacks and coffee around, so take a look around to find the snacks. And at 2 p.m., before, at 1:30 p.m., we're going to have a talk by Agnostic. They're going to talk about their platform, Covalent, so platform agnostic accelerated computing on cloud with Covalent. And then we're going to have a very exciting panel. I am very, very excited about this panel. It's called Employed/Unemployed, and it's all about talking about careers in quantum. So everybody who's here, you're probably interested in this topic, hopefully, right? So definitely join the panel, hear what the speakers have to say. We have Anastasia Marchenkova. So I don't know if you're here already. No? Okay. All right, we have Anastasia Marchenkova, Roger Luo, Richard Graham, and Jake Maliaros. So excellent, excellent panelists. And then we're going to have additional workshops, a workshop on working with Penny Lane datasets by our very own Diego Guala, and a Quantum Careers Masterclass by Aaron Walker, who's in our HR team. Now, throughout all of this time, after 11 a.m. when the hackathon description is going to be revealed, you're going to have a drop-in coding support, which means there's going to be always somebody from Xanadu behind the kitchen. So between here and Olivia, they're going to be there available to help you with code support if you need it for your hackathon project. We're just going to have a little break from 3 to 4, but otherwise, you're going to have hackathon support. All right, these are like the announcements. Bathrooms are located to my right, so to your left. Right behind these meeting rooms, you're going to see some lockers, and right in front of them, there's the men's bathroom and the gender-neutral bathroom, which today is also going to be the women's bathroom because we're having some tech issues there on the actual women's bathroom. It's okay. It's okay. We still have bathrooms. So we're gonna use the accessible bathroom and the gender-neutral bathroom for women's bathroom today as well. Isaac, what did I miss?
Nothing. I think that about covers it. I don't know. I've been focusing on other things here, so. But
All right, perfect. So everybody in the stream, stay tuned. Definitely do not miss Nathan's keynote. Don't miss Katharine's talk by AWS. And don't miss the panel. I'm really excited about all of these events that we're going to have streamed today. There's more coming tomorrow. So this is just the agenda for today. But tomorrow there's more exciting stuff going to happen. So I hope everybody here can also join tomorrow. I know that some people come from different companies working in quantum computing. So definitely tell your companies that this is a place to be these 2 days.
oh, I actually do have one thing. For people online on Twitch, we'll be having a giveaway for like swag after Nathan's talk at 11. So if you're just active in the chat, you're entered in the giveaway pretty much. So, you know, spam, random stuff, doesn't matter. And then one of our moderators will get in contact with you. And yeah, that's pretty much it from my side.
Yeah. But now that you mentioned spam, please don't spam. So we do have a code of conduct. Definitely follow the code of conduct. Be nice to everybody, virtually on site everywhere. If you don't know what the code of conduct is, it's probably printed out like everywhere on the website. You can go to QHack.ai and just like general, normal, be nice to everybody. Awesome. So virtual people, 15 minutes back on the Twitch, and on-site people, 15 minutes to walk around, find your way, and then, yeah, come to the keynote.
All right, everybody. We are going to have Nathan give his talk right now. So get your eyes peeled, your snack in hand, coffee. We're going to get going here. Again, Nathan's been here at Xanadu for quite some time. Louder? Even louder. I guess I have it on my headphones too, so I just hear myself at all angles. So Nathan's been here at Xanadu for like basically since day one. Actually, we chatted a little bit about his early times at Xanadu and like early times in Penny Lane on our YouTube channel. So we have a little podcast episode on that if you want to check it out. Not right now, obviously. Nathan, you're going to talk to us about better than classical ? The subtle art of benchmarking. Oh, and it'll be on archive soon. Cool. Something to look forward to. Take it away, man.
Thank you, Isaac, and thanks everyone for coming today. It's really, really cool for me personally to see people back on site for QHack. The very first QHack, as was mentioned earlier, was at our office here in downtown Toronto, upstairs, and that was in 2019. And so it's really nice to welcome everyone back and to see all these faces in person. And I hope that you can enjoy our office space, enjoy talking to our team, and I'm looking forward to meeting all of you. So today I'm going to give a talk that represents some of our current thinking about the field of QML, and maybe it's a bit more critical than some other works out there. So I want to maybe just cause people to think a little bit more carefully about the fields. My goal here is not to provoke, but maybe to just inspire you to be thoughtful about the papers you read. So there will actually be a paper representing this talk on the archive soon. The paper's coming together. It should be out in the next month or so. So watch for that. So everything here is preliminary results, a sneak preview. The main message of the paper is not going to change between now and then, but some of the final data might come in or be improved. We've got lots of great quantum machine learning researchers here at Xanadu across a couple teams. I myself contribute, but we also have a number of strong people on the team. This particular project that I'm speaking about today represents the work of Joseph, Shahnawaz, and Maria primarily. They're the ones who are doing a lot of the really hard stuff here to bring these results to us. So full credit to them. I'm representing their work today. Generally, it's really easy to say, well, QML research, the goal of QML research is to make quantum computers useful for machine learning. That's very, very, pie in the sky kind of way of thinking about it. But when quantum computers were first dreamt of in the 90s, let's say, the state of play for computer science, for programming, for just computers in general was much different than it is today. By the time quantum computers are reaching a large-scale, fault-tolerant regime, the surrounding background of computer science and computing technology that they find themselves in will have drastically shifted. There's a huge, huge growth in AI, in machine learning. These kind of things are going to be, background standard stuff that everyone learns about and everyone kind of takes for granted. So we should make sure that quantum computing fits nicely into that world it's going to emerge within. So quantum machine learning, that's why we pursue quantum machine learning here at Xanadu. We think it's going to be kind of essential ingredient if we're working on quantum computers, and computers are going to be pretty highly connected with machine learning ideas. QML is a very, very broad field. It can mean lots of things. Just to really simplify scope, we're just going to talk here about the notion of solving machine learning problems using quantum computers. There's other ways you could kind of combine machine learning and quantum, but that's what we're going to talk about here. And then we can break that down into kind of two main schools of thought. There's the subset of algorithms that work on fault-tolerant quantum computers. These are kind of idealized quantum computers. You can imagine any number of qubits you want, full error correction. These, there's lots of papers of these historically. The general trend is maybe to take a part of a machine learning computation, and outsource that to a quantum computer. That's the general flavor of these kind of fault-tolerant subroutines. And then more recently, we have this NISQ era, which may be hitting the end of its peak. The real trend setter in the NISQ era was these variational circuits. These are quantum circuits where the quantum circuit itself is the model. It's not just outsourcing a subroutine of a larger pipeline, but it itself is the model, or a significant portion of it. And we study the properties of these quantum circuits as machine learning models or through a machine learning lens. So how do we know if we're researching the right things, if we're making progress, right? In AI, they have tons of data sets, they have huge compute power, they have real-world problems that they can test things on at scale. We don't have that in quantum machine learning. We're stuck with some other tools that are maybe giving a more imperfect glimpse into things. So if you look through the literature, you'll see probably two approaches to kind of vetting our ideas. One is, well, let's prove there's something interesting happening here. Let's prove some scaling, some speed up, some efficiency gain, some advantage. Let's prove that on paper, right? And these on-paper settings might be quite divorced from real-world use cases if we ever reach them. You'll also see, and this is nice, the kind of emergence of quantum software has allowed people to run benchmarks, run numerical experiments on their ideas. So not just proposing an idea, running some lines of math, but we can also write some lines of code to try to vet the ideas that we're proposing in our papers. These are typically pretty small scale because quantum systems that we can simulate right now are pretty small scale. Quantum hardware that we have access to is pretty small scale. So these are small scale benchmarks, usually confined to a single paper testing its own results, and that's it. There's not a lot of reproducibility going on. So this is how it currently exists. I'm going to focus more on the benchmark side in this talk. And in fact, taking benchmarks from just single paper, what I call single paper benchmarks, to more of like meta-study. Let's actually test a whole bunch of different numerics from different papers and compare them to each other. So if we're going to dig into the question of benchmarks, and when I say the benchmarks here, I basically mean like numerical experiments, running code either on a quantum computer or on a quantum simulator to test an idea, to validate that the idea is doing something interesting. Right? How can we, or can we even trust the benchmarks that we see in the literature already? Can we trust what we're seeing in papers? Interesting to do a kind of a small little experiment. We can search on the archive for, what do we search for here? So search for papers from the quantum physics sections of the archive, searched for the terms quantum machine learning, and then kind of a wild card on outperform. So let's look for any papers that use the word outperform plus quantum machine learning. And we found about 73 results there. I should say that using other kinds of words like better than or advantage, kind of similar results to this search. So we found 73 papers. You can break them down, but 20 we ruled out because they're just using very, very generic usage of the word outperform. Like QML is expected to outperform classical, maybe a very forward-looking statement. It's not really too concrete a thing to put scrutiny on. But then the remaining papers, they're actually talking about comparing to other models, other algorithms. So 28 of those, better than some other quantum method, right? So my turbo VQE is better than vanilla VQE. That's that kind of paper. So we found 28 of those. And then 22 papers that claim to be better than classical, right? This is amazing news, right? If we're better than classical, then that's the holy grail. Well, 22 papers are already claiming it, right? That's maybe something to be skeptical of. Found 3 papers that actually were willing to admit that they were worse than classical, right? And even on closer inspection, 2 of those papers were kind of hedging their bets a little bit. They were saying, well, if hardware wasn't as noisy, we'd be better. Or once we get quantum computers of sufficient quality, we should be better. There was only one paper out of this kind of quick and dirty search that actually just unequivocally stated, our idea is worse than classical, right? it's maybe not so surprising, right? We're incentivized to put forward positive spin, positive results on our work. That's the whole kind of the game we're playing in some sense. So yeah, there's good reason to be skeptical. There's obviously a lot of positivity if you just kind of look at the literature. And one of the messages I want to communicate here is don't take any, don't infer too much from just the positivity you might see in the literature that's fact. You know, we should back these things up with more large-scale tests and verification and validation. So there's actually growing skepticism as well in the non-quantum machine learning community about these things. There they actually have better tools than us to test because they have larger data sets and larger compute power. There's way more papers, so they can actually maybe look at the trends a bit more. There's clearly benefit and value in classical machine learning. It's doing something interesting for sure. But on the level of individual papers and claims made in individual papers, you want to be careful because things to keep in mind, the results of a numerical experiment may change under a whole number of factors, a whole bunch of different degrees of freedoms that you could choose to do B instead of A can potentially lead to different results. Right, so it tells you about potentially how brittle some of the results might be. So, for example, if we select a different task, then a particular model may not perform very good. If we correct for human labeling errors, we might actually not see the same performance we saw otherwise. If we use different training and test set splits for our machine learning problem, we might see a different performance. If we try to even just reproduce studies that are already out there, we might not get the same results that they report, right? So some of these results are not even reproducible. Sometimes we need to maybe use a more fair comparison, right? And if we use a more fair comparison, things don't add up anymore. There's this notion of hyperparameter optimization. There's lots of things that you kind of have to freeze in order to train a machine learning model. Well, what if you froze it to a different value? Or what if you spend more time searching for overall possible different values? You might see different performance. If you use a different scoring metric, if you don't just use accuracy but use something else, again, potentially you might change the results. If you factor in other computational costs, maybe the advantage goes away. And then this is maybe the biggest one. This is kind of leans into our study the most. There's a natural tendency in the game of science to have a positivity bias. The scientific method doesn't tell us anything about, we should be positive or negative about things. It just, you have a hypothesis and you test it, right? But in the game of science, what gets reported? What gets reported is the exciting stuff. What gets reported is the stuff that, advances our careers, makes us look like we're, putting forward exciting, interesting ideas. The null results don't always get reported. The poor results don't always get reported. And things are often not validated. So that initial positive cherry-picked result never gets kind of new data added to reweight it. So all of these things can potentially change the performance of a model. So what that means is we should gauge the performance of models, of machine learning algorithms, by varying a whole bunch of these things and seeing how well they continue to do, how robust they are, how specific or generic their powers are. So our team had the ambition, the goal, to do a large-scale independent benchmark study with the intent of judging if near-term quantum machine learning models will be useful for generic machine learning tasks. So taking a view of the literature and trying to draw some conclusions about that by testing models pulled from the literature, implementing them, and testing them on various different benchmarks and data sets. So kind of before you even get to the stage where you're testing models, there's a lot of work to do to draw up the playbook, right? The rules for the study. You can't just do it too haphazardly. You have to be careful what you're doing. And there's a lot of work behind this. It's maybe not appreciated when you see at the end result, hey, we chose A, B, C, D, and E as our criteria. actually coming up, are those things fair to choose? That's quite difficult. So there's lots of considerations to keep in mind even before we start looking at running things through the benchmarks. Okay, so first thing, what are we going to benchmark? There's lots of ideas out in the literature. There's lots of different tasks and problem classes. What are we going to focus on? We have to focus on a subset, right? So we decided to focus on quantum machine learning models that are used for classification. Okay, so not a generative problem, but like classification. Is it a dog or a cat? These kind of problems. Our starting point was the archive. We started after 2018. And the reason for this is kind of when the NISC era, the variational circuits era, kind of kick-started. So we wanted to kind of focus on those class of algorithms because those are the ones that are generating a lot of text about. Put in certain keywords, classification, learn, supervised, and NISC. This ended up getting 3,500 papers. That's way too much to test, especially when you're having to re-implement a lot of the code before you even start. The code's not often available. So we have to downsample pretty dramatically still. So we decided to have some sort of arbitrary cutoff here towards influential papers, I'll call them. These are papers that are more than 30 Google Scholar citations. So these are naturally going to be biased towards more recent papers and papers that are cited a lot. But those are kind of the papers that do influence people's thinking. People will start to hear these things and think that these are established ideas. So we wanted to focus on those. So that gets us down to 561. Then of those papers, let's focus on ones that propose a new model. So not just work going back over old ideas and revising them, but something that proposes something new. And it should be a quantum model for classification on classical data, so no quantum data here. That gets us to 29. That's almost manageable. Decided to downsample that down to 15 papers randomly, just to give a random selection. Upon closer investigation, it turns out that's only 11 of those papers were things that we could actually kind of legitimately or fairly implement, or that we thought should still qualify. So there might have been one or two papers that, if we were more careful, we would have selected out earlier in the process. For instance, there was one paper that actually, upon closer reading, was working on quantum data, even though that was one of the criteria we were supposed to filter for. So we ended up with 11 papers. So a couple of them got dropped in this last stage for implementation reasons. And then there was one of the papers that actually proposed two distinct architectures that are based on the same idea. So out of that paper, we had 2 models, and then from the remaining papers, we had 1 model each. So we ended up with 12 quantum models for our study. Here's a kind of a high-level overview of all of these. Don't worry too much about reading the text, but it's split into 3 classes. There are the QNN class, the quantum neural network class, the quantum kernels class, and the quantum convolutional models class. So quantum neural network is basically your standard variational circuit. If you know the literature, it's upload some classical data somehow into a quantum circuit, run a circuit that has free parameters, train those parameters to achieve some low-cost function value. The quantum kernels papers, or models, they have the structure where you put in use a quantum circuit basically to generate what's called a feature vector. And these feature vectors are used then just downstream in a classical machine learning pipeline, a kernel methods pipeline. So the quantum circuits are used basically just a feature embedding. And then the convolution ones, these are ones where we actually have a quantum version of a convolutional model. So a convolutional model is a standard neural network architecture typically used for image processing. So these are the quantum versions of those ones. So those are the 3 classes. I don't know if everyone can read it, but you'll recognize probably quite a few kind of standard ideas that have been out there for a while. There's a few Xanadu papers in here. I think there's 1, 2, There's 3 papers from ours, so we're not exempt from any conclusions here as well. So these are our combatants to enter the arena. Okay. Now, once we have our combatants, who are their opponents? Who are we comparing them against? Well, we decided to choose 3 classical models to kind of match those 3 categories: the neural networks, the kernels, and the convolutions. So we chose 3 classical models, and we chose kind of standard models. We didn't choose any sort of fancy models here. We didn't make any efforts to do like a fair comparison. We just chose like, what is a standard tool that someone from classical machine learning would apply to this kind of problem? Okay, so a multi-layer perceptron classifier just out of scikit-learn, just a kind of generic one. It's the bare bones neural network vanilla architecture. There's a support vector classifier. This is a pretty prototypical kernel method type model. And then a convolutional neural network. That's a natural comparison for the quantum convolutional models. So these are all super, super standard models in classical machine learning. And we just want to see how do we compare against the out-of-the-box models. Okay, so we've got our combatants. How is the victor to be judged? How do we know who's winning or who's losing in the battle? Well, we need a problem that they're competing against each other on. So we ended up choosing 5 problem classes. They're all similar in that they are focused on binary classification. So is it a dog or is it a cat? Just 2 choices for the classification. And for training, we use the accuracy as a figure of merit. Okay, but then we have 5 problem classes. So there's a very, very simple one. It's literally just in n dimensions, draw a n-1 dimensional hyperplane. So split n dimensions into 2 half spaces. Everything in the one side is class A, everything on the other side is class B. That's how you generate that data set, and you can obviously work in different dimensions, and you can have different hyperplanes that you use to generate the data. So that's very, very simple. It's just a standard linear machine learning model should be able to completely separate those 2 classes with perfect accuracy. We used MNIST. I don't know if MNIST is the greatest thing to use for quantum machine learning, but it appears in so many papers that we kind of had to include it just for comparison purposes. We did pre-process it. MNIST doesn't typically fit into a quantum circuit that we can simulate or run on hardware, so we had to pre-process it. So we used principal components analysis to kind of downsample the dimensions there and vary the different dimensions that were available. And then we included 3 more theory-inspired data sets. So these are 2 of them are from the machine learning literature. There's this hidden manifold type of data. Basically, you generate a big cluster of data, you split it into 2 classes, and then you embed that in a higher dimensional space. We also have a 2 curves kind of problem class. Here you have some curve that kind of defines the shape of your data, and you sample points near that curve to generate the data. And then to get the second class, you do the exact same curve, but you just displace it by a little bit. And then you embed both of those 2 different classes of data into a higher dimensional space. So basically 2 squiggly lines in a larger space. And then the last one, this is one we made up ourselves. It tests a more global property, and actually it should be a challenging one, the parity of hyperplanes. So you need to know in high dimensions which side of a hyperplane you're on. Okay, so those are the 5 different problem classes. And then from those problem classes, there's a few degrees of freedom still available to us. So how many dimensions the data is, for instance, is something that we can tweak. So this allows us to kind of vary some parameters, vary these degrees of freedom, and create multiple data sets of the same problem class of varying degree of complexity. So using all those components together, we ended up generating 155 different data sets. So we have, 12 models and 155 data sets. So the servers have been humming in the background for months now to generate all the data for this talk, because there's a lot of experiments to run, and on top of that you have to do this hyperparameter search. So there's really just a lot of numerics to back up what we'll just see here is just a few small figures. So those are our problems that we're working with. Okay, there's still a few more decisions that need to be made before we can conduct the study. You want to make these decisions in advance because you don't want to be making them ad hoc as the study is ongoing, because that can bias the earlier ones versus the later ones. So these decisions have to be made more upfront. Just to maybe spell out some of the things that you have to think about. When we work with papers, it's obvious, there's always a paper, but it's not always a code available for the paper, or the code doesn't quite match the claims in the paper, or if there's, maybe there's different examples that they had, and they don't all allow us to compare it against other models, or it doesn't obviously fit into the 155 data sets that we've created. So there's always some tweaks needed, always some implementation things needed. We tried wherever possible to be as faithful as possible to the existing code, to the existing papers, but there's some decisions that had to be made, and we just tried to use common sense whenever possible to fill in the blanks. Some models take a lot longer to converge than others, so you have to maybe set some criteria. We just basically let them take as long as they needed. We just waited until they settled in and stopped changing after a couple intervals, and then we said, okay, you're done training. But some might take 30 seconds, some might take an hour, and we let them take as long as they needed. We didn't factor in training time as kind of way to limit models. You might have to do this hyperparameter batch size. When you're doing stochastic gradient descent, you have to choose what are the size of the batches that you're stochastically selecting from the data set. We didn't optimize this hyperparameter, but we actually had to use it as a way to control the length of computations, because if you keep it too big, some of these computations take way too long. So this is one that we kind of kept in our back pockets. It's not optimized for best performance of the model. It's optimized for just numerical implementation reasons. Sometimes there's data preprocessing needed. We tried to preprocess and scale things into some meaningful interval whenever possible. And then you have these choice of hyperparameters. Despite your model being fixed, there may be still a few free parameters that need to be chosen for a particular experiment. And ideally, you should iterate over these and test if I fix this one hyperparameter, and I train the model, and I look at its performance, and then I change that hyperparameter, and I train the model, I look at the performance, what's the best choice out of all of those experiments? So we had to kind of make a grid to search over all these different permutations, and we tried to take choices that are relevant to the paper, tried to use common sense, and also, again, this is one of those things where we had to eventually set a limit on the runtime, so we can't do a super exhaustive search. So those are the kind of things that you'll have to take into account when you're designing a benchmark study. Maybe just as a quick teaser now, the hyperparameter optimization actually, these are results. Don't read too much into the numbers here, but just look at the size of those bands. So what those bands indicate is the best performing model versus the worst performing model for the same model type. So it might be a very specific model from one specific paper, but we change the hyperparameters and we look at the performance, and you might get between a random coin flip all the way up to perfect accuracy. So it's quite important to do hyperparameter optimization. I don't think most people are doing those in their own papers, but it turns out it's quite important, because the performance claims that you can make are really dependent on your choice of hyperparameters, as we can see by the large spread here. All right, so that's all the setup. Now we can get into the actual results. What did we find? So the way I'm going to present this, we have 155 different data sets, and we have 12 different models, and then we have 3 classical machine learning models. So I'm going to treat it like the Olympics. So we have the Olympics, you have maybe 500 events, right? And you have 150 countries participating. So our models are going to be the countries, and the events are going to be the different benchmark data sets that they're run on. And so who wins? Well, the one who has the most gold medals is usually categorized as the country who's won the Olympics, right? They have a ranking in the online or on the newspaper that says, Canada has 12 gold medals and 8 silver medals and 6 bronze medals. So that's how we're going to kind of compare models to each other, is who's winning the most gold medals. That tells us which models are kind of most generically powerful versus ones which maybe just won that one esoteric medal in breakdancing. Okay, so these are kind of the ranked results split into 3 classes. So there's the kind of neural network class, the support vector machine class, and then the convolutional class. The real main thing to notice here is the top line is the best. It's always the classical one. So the one with the biggest green bar is always going to be the classical model. That's what we've discovered. That's kind of our first takeaway here. Some quantum models actually did okay. They won a fair share of events. So that's cool. Some of the quantum models may be doing something interesting, right? Some of them did really bad, and you probably are not going to be contenders for, even making the cut for the Olympics next time. So that's kind of the main takeaway for this slide, is that the pretty out-of-the-box classical models over a wide class of problems, sizes, and types, they performed generically better than the quantum models. Getting a bit more into some of the data here. So we've got one of the data sets, the linearly separable data set. On the left side, we show the quantum neural network class. On the right-hand side, we show the support vector machine class. The lines at the top are the classical models, and the x-axis going from left to right is basically the dimension of the data sets. So it kind of gets harder and harder as you go along. But you can see that the quantum models actually get poorer and poorer as you get higher dimensions. So if people are only running small-scale benchmark experiments, they don't go up to higher dimensions, they may make false conclusions about the power of their model. This is on the MNIST data sets. So the left one is this neural network class, the right one is the support vector machine class. Again, we see the classical model at the top, and kind of the performance peaks for all the other models, except that's tree tensor classifier, which doesn't seem to be doing well at the bottom there. I should say these are kind of representative benchmarks. Other benchmarks that I'm not showing you give very similar types of results. This is the last problem, which was hyperplane, the problem. This is one where I actually expect by design that both classical and quantum models are going to do poorly. So we kind of designed this one to be difficult as the dimension scales up, or as the number of hyperplanes in this case scales up. And it's kind of what we see. The classical model still generically is the black one on top there. There's a few peaks where the quantum model might pass over and do slightly better for one particular dimension, but then it oscillates back down again. So the main takeaway here is even though there's some variations, the picture is generically consistent, that the quantum models don't do well as you scale up, and also similarly the classical models do the best. Okay, so those are the results. If you're interested in more and more in-depth stuff, we'll be sharing all the data, we'll be sharing all the benchmarks and the code for running those things. The last part of the talk I want to get into, what is going to happen next, right? We've done some studies. I think the purpose of benchmarking should be to make us question our assumptions, but also it can reveal things that we may not have thought about otherwise, because we're testing things in a richer manner than we would have done otherwise. So the benchmarks actually do reveal some interesting open questions which one can consider for follow-up. And we'll have the data all available, and if other people want to look into the data and find their own open questions, we encourage people, because we don't want to be completely doom and gloom and say that classical models are just hard to beat and we haven't done a good job yet. There's some interesting data points here that are maybe worth following up on. Okay, so one question someone might say, it's often claimed that entanglement is one of these mysterious quantities in quantum computing, and that's why we expect QML to do interesting, advantageous stuff, because it has access to entanglement. Did a very simple follow-up experiment where we created a model that was just a standard variational circuit, so a quantum circuit with gates and measurements. And those gates are parametrized, and you can tune the parameters to minimize the cost function. But the structure of the circuit was such that there was no entanglement generated. So the gates are only ever being applied on the single qubit level. No qubit ever interacts with any other qubit. Well, how does that model do? Not bad, actually. It turns out it does better than some of the other fancier quantum models. So that's interesting. That's something to maybe generate some follow-up questions, right? Why, if we're always claiming that entanglement is this important, crucial ingredient for quantum models, why does removing it do little harm? So if you're looking carefully at this graph, maybe it's hard to see the colors from far away, but there's a couple quantum models in there that are between that separable classifier and the fully classical one. Right, so what about those two? They seem to be doing all right. They're almost doing as good as the classical model, and they're doing better than the unentangled one, so surely some entanglement is crucial there. Well, you take those two models, they're very specific ones. They're the dressed circuits model and the data re-uploading model, two kind of standard models you see in the literature. And you'll take those architectures and just remove the entanglement. What happens? Well, for the dressed quantum circuit classifier, turns out it doesn't change the performance at all, so that one doesn't seem to be relying on entanglement. The data re-uploading classifier actually does get worse. So that one maybe seems to be using entanglement somehow for its performance. Still not beating classical, but maybe there's something there to that idea that we're hearing in the literature that entanglement is important. But only for this model. It doesn't seem to be validated for some of the other models. Okay, so what makes that data re-uploading model kind of successful? This is actually one of the earlier models proposed. It has a couple unique ingredients that distinguish it from other models. It has a circuit that looks like this, and you alternate between uploading your input data and having a parametrized layer in your circuit. So X is the input data, theta is the parameter, and you alternate. That's why it's called re-uploading. So that's one unique feature here. Another unique feature, and this was surprising to me that more models don't do this, but they include that you can reweight the data as you're uploading it. You can have a parametrized weight attached to each data point. The third kind of unique ingredient here is they use a specific cost function that's not too common in the rest of the literature. Okay, so you can perform a study on that and say, well, those are the three ingredients. What happens if we remove those, right? Let's do an ablation study. So looking at the results, turns out if you remove the cost function, the special cost function, and you put a standard cost function there, it doesn't really change the performance. So that one doesn't seem to be too important for performance. However, if you remove either the scaling that you're doing to the uploaded data, the trainable scaling, or if you're removing this kind of re-uploading structure where you alternate and you just do all of your data upload all at once and then all your parameters at the end and you don't cycle back and forth, if you remove that, it also hurts performance. So those kind of hinted, well, those are two interesting ingredients here, right? Those are actually responsible partially for the performance. That's an interesting open question, right? That's something that came out of the benchmarking study. By looking a bit closer on these models, we can actually try to understand, of all the random ingredients that a model might have, which are the ones that are actually doing something interesting. There was the other model there, the dressed quantum circuit classifier. This one's a funny one. You basically take a neural network that's pre-trained and you chop out like a middle layer and you replace the middle layer with a quantum circuit. And my conclusion to this model is that doing that doesn't hurt anything because the performance of the model ends up kind of being the same in the end. It's maybe not too surprising because there's so much huge work being done by the rest of the layers there, and the quantum circuit is just kind of, it's not hurting anything by passing through it, but it's not contributing anything. So yeah, we can say, well, that's kind of a prototypical hybrid model. So do quantum layers and hybrid models, are they doing something interesting or are they doing something kind of standard? So what we did is we looked at all the different layers of the model, and then we also looked at the comparable structure without the quantum circuit removed and look at all the layers there. And we kind of mapped in low dimensions what's happening to the data set as you go through each layer. So the one I want to draw your attention to is this one here. This is kind of where the quantum layer is inserted or not inserted on the bottom one there. And we can see they're slightly different. They're qualitatively doing something slightly different, but not too different, right? They're still able to separate the red and the blue curves. They're not mixing them up too much. Actually, the quantum one is maybe doing it a bit more, but it's not something that the final layer of the neural network can't recover from. As we see in the last column there, it's easily able to recover from that. So that's why it doesn't hurt. So again, this is one of those things where you can do studies to compare by just removing certain components of a model rather than comparing your full model versus a fully classical model. Final open question could be that sometimes the quantum kernel methods actually perform somewhat similarly to the classical models. And why is that? Well, this is another one where we kind of looked at it a bit more. This is in 2 dimensions. These are kernel models, so we can look at a kernel function, which is a 2-dimensional function. And on the left column is the classical one, and then all the right columns are the quantum ones. And we can see in the first row that they're all kind of the same shape. So that's probably why they perform similarly, because they have the same kind of structure to them. The lower one's a bit different. You can see that the quantum models start to do more and more funky things there that are quite different, more spiky, especially the projected quantum kernel model. So this at least reveals some sort of specific property of that model that warrants further study. It's doing something different than the classical model. I should say in higher dimensions, these things don't map so nicely. So also it might be something that's different between low dimensions and higher dimensions. They're not, they're not looking exactly the same in higher dimensions. So again, open questions that doing these studies more systematically can help unearth and can help us understand these models better. So just to conclude, I want to give you the key takeaways from this talk. Number one, full credit to our team. Designing good benchmarking studies it's hard work. It's nasty work. It's not fun. But we're happy to do it because if it helps move the field forward, it helps people thinking and seeing the right things, it's worthwhile. Next point, this is probably the only one that people will take away, I would guess. Classical models, standard ones, typically outperform even the most influential quantum models. So there's still lots of work to do here to really make our case. Another one, that fancy phenomenon of entanglement. I don't know if we can make the case that it's doing anything. We can always appeal to it, but the numerics do not necessarily back it up yet. We need to make a stronger case that that's to hold. And there might be some models where we can show that. And then doing this kind of benchmarking, I think, helps us move the field forward because we're not just focused on what's a cool new idea, but actually what's a valid idea? What's an idea that's working, right? And then maybe it's the more boring march of science doing this, but I think it's more important for the field because otherwise you end up being disillusioned if you end up working on all these ideas, but they're on paper, they don't actually work in practice. So I'd rather know that in advance, I'd rather know that soon, rather than working on false assumptions. So definitely doing benchmarking studies like this is important for science, is important for QML, and we hope it can help advance the field's thinking in the future. Thank you very much.
Cool. All right. Thanks, Nathan. That was good. We're going to get some questions from the in-person audience. So, yeah, raise your hand if you have a question, and Catalina will hand you a mic. Catalina, do you want to just make sure that one works? Turn it on and...
Test.
Hey,
yes.
Sweet.
Hello. So I was curious, you said in the conclusion that entanglement is not very interesting and it doesn't really change the model, if I understood right. Yes?
More or less, yeah.
But I was curious and more like the study was for accuracy, but in other terms like robustness against adversarial attacks or generalization, would you think that entanglement would help in those terms?
To be honest, I don't know. I mean, I think this is the kind of thing that's we can test. We can try to look at measures for those quantities and see. We've got all the models built now. We can just test those entangled models and non-entangled models against those. I would find it hard to predict, to be honest. Like, I would say removing entanglement, I would guess. I don't have much intuition whether having entanglement there makes it more robust.
Yeah. But because I was curious, like it was just analyzed in terms of accuracy, but maybe entanglement or like hybrid networks, like you were saying that there wasn't much change, but maybe those evaluation technique or like a robustness and things like that would increase.
Yeah, absolutely. It's a valid hypothesis, and we'll have all the data, all these models available, and it's something that people can test. So I encourage people to check that out if they have that hypothesis.
All right. Thank you.
Hey, so I know you talked about the MNIST data set, and obviously you were compressing it or basically downscaling it a lot so you could actually make it fit in the machine. But do you think that if basically you were able to encode more data, would the performance be, do you think it would be better, or would it be possible for it to be better, or do you think that's kind of just, would it just like comparably to a classical system at that point? Because obviously it kind of did worse at this point, but you're losing a lot of data just in downsampling, so.
For sure. I think we can kind of infer from this slide here that the quantum models aren't getting any worse as we're increasing so the x-axis here is basically equivalent to like how much we downscale the images and how much information we include. So they're not getting worse. They're not getting so much better either. And that's because when you're doing this principal component analysis to downsample the image, it's kind of marginal gains every extra dimension. Most of the information in MNIST is in the first 5 degrees of freedom or something like that. So yeah, it should get better, but maybe just marginally.
Okay.
Yeah, so Catalina's coming around with the mic for you there.
Hi. So have you tried changing like some of like your crucial decisions, like convergence criteria, and see how, like the results change, or if like the entanglement properties, like how they changing the convergence, or for example convergence criteria, or like some of those crucial decisions can affect those results like as well.
Yeah, to answer the question, no, we haven't specifically gone back and rerun a new set of benchmarks with those criteria now switched. There were some things we kept fixed and some things we didn't. But we did initially start, there are some decisions you can only kind of come to by getting your hands dirty with the data.
I mean, obviously, just certain.
Yeah,
decisions.
so there was some early just digging into the data a little bit to help infer what decisions we should make, to help uncover those crucial decisions. But then once we did, they were locked in for the rest of the study.
Oh, okay. Thank you so much.
So to perform the QML algorithms, were they either performed on a simulator or an actual quantum computer?
Yep, all on pure state simulators.
And so, okay, that was my question. So the assumption was there was no noise doing this. Okay.
Correct. Maybe one last question, yeah?
Can you elaborate on the case where you said the data set is more difficult for classical machine learning as well? Like, to what extent, what make it more difficult? And whether, like, depending on the problem set you're working on, maybe some cases QML could perform better. It's just a lot of the cases you're testing on is already working well in classical machine learning.
Great, thanks for the question. See if I can find my slide here. So the data set you're referring to is this parity of hyperplanes one. And the reason this one is expected to be difficult for classical and quantum is that it's parity is like a global property, and it requires kind of global information. And so with limited data, it's hard to make a good guess there. So that's kind of unique to both classical and quantum. It's not something we would expect either one necessarily to perform better at. The hidden manifold and the two curves, these are just pretty generic ones. These are not specifically designed for like real world data. These are kind of just to test test settings that are believed to hold about any sort of structured data, right? So I would say the main thing that's maybe is not specifically represented here is what if there is like a quantum data. So like a data that specifically showed correlations that were expected to be good for a quantum computer to do. Yeah, it wasn't included, but that's a good suggestion, yeah.
Okay, we'll get one question from the chat here, and then we'll have to wrap it up.
Sorry, guys.
So we have a question on Twitch from D'Amelio. One thing that is not entirely clear to me is the quantum classical comparison done to see how quantum-inspired models work instead of using actual quantum circuits? We know that data encoding is expensive, so why are quantum models helpful to classify classical data?
Well, maybe they aren't helpful. That's maybe something a lot of people might tell you. Maybe that's a conclusion that can be made, right? If it merits further investigation, but maybe these are the wrong types of problems to be probing quantum models on, right? And I've talked to a number of people who, they're strongly inclined to dig into, well, I think quantum data is the real kind of killer app for QML, and that's a completely fair hypothesis, and I kind of share that belief.
Okay, cool. Well, one last round of applause for Nathan. Thanks so much, Nathan. Really appreciate your time here. We have Katharine Hyatt from AWS coming up in about 10 minutes, so maybe just get some coffee, whatever, sit tight. For those online, we'll be doing a giveaway, but yes, sit tight, and we will be back shortly. Okay, everybody, we are going to get going here. So round up your coffee and find your seat. We're going to hear from Katie from AWS. Katie, you've how many QHacks have you been in?
I've presented it 2 and been support for 4, I think.
Okay.
It's a lot.
It is a lot, yeah. I think I remember last year, actually, during your talk, that was when our stream died. And we had you were wearing your cat headphones.
I was.
And there was there was interesting poses from myself, or it was Catalina that was hosting last year. And yeah, anyway, fun memories from last year. All right, so yeah, Katie, thanks for joining us today. Really appreciate it. How many people have asked you about a QHack related question, and you've had to point them to a person with a purple shirt today?
I'd say around 10.
Around 10?
I guess that means I look credible. They're like, this person probably knows what they're talking about, which is always a big mistake to assume that.
All right, well, we're here to listen to what you know to talk about, which is hill climbing and valley crossing. So take it away, Katie.
Great. Thank you so much, Isaac. And thank you to all the organizers of QHack for putting on this great event year after year. I think every year Amazon's participated. It's gotten better. And also thank you to all the attendees for showing up, especially because this event started pretty early on a Thursday. So today I'm going to be talking about some ongoing work we're doing on the Amazon Bracket team, and also kind of an overview of some of the challenges in the field of using near-term quantum devices for quantum chemistry. I'm really grateful that I'm going right after Nathan, who gave such a good introduction to why benchmarking is really important, and also the importance of being realistic about sort of the challenges that are facing our field, where there's a lot of promise for these technologies, but we also have to be honest about sort of what the difficulties we're going to encounter are. So the first thing we're going to talk about is just a quick overview of the variational quantum eigensolver, perhaps for folks who haven't had enough coffee yet this morning or they haven't been exposed to it. We're going to talk about sort of the general way people apply this technique and some of the challenges, and then talk about the project we're doing to benchmark how well some possible solutions to this might help us. So for folks who aren't as familiar, perhaps, with near-term intermediate-scale quantum algorithms, the variational quantum eigensolver, as the name implies, is an algorithm for non-fault-tolerant quantum devices to find low-lying eigenstates, or indeed any eigenstate. There's lots of applications of this, but one arena in which it's very popular is quantum chemistry, because finding the ground state of generic molecules is, in general, a pretty difficult problem, even for classical computers, and there's lots of applications for it. So the general recipe for applying this technique is that we encode some second quantized Hamiltonian of a chemical system as a kind of digital polysentence that we will then run on a quantum computer. We build up an ansatz, which consists of some initial basis state guess in this second quantized occupation basis. And then you apply parameterized excitations to try and improve your ansatz as you go, and you optimize these parameters. And hopefully at the end, you end up with a reasonably good approximation of the chemical ground state. And so there's a bunch of different procedures we'll need to apply here to actually do this. The first one is just even writing down our Hamiltonian. So we start off with the famous many-body Hamiltonian for a chemical system, where you've got both the kinetic energy and the potential energy interactions between all the constituent particles in the molecule. And we have to turn this somehow into a discrete Hamiltonian that we're going to actually execute on some qubits. And so already we have a lot of freedom in how we do this. Generally, the way this is done is that you pick some sort of orthonormal basis of functions in the regular first quantized space, and then you integrate over those to generate an occupation number basis that you can then write for the quantum computer. So this is something that is kind of a well-described process, but even the initial first step of picking those basis state functions gives you a lot of freedom. And then, once you've chosen those, you have to figure out how you're going to actually encode this occupation number basis, because the constituent particles we're interested in, electrons, are fermions. And so we then have to choose, are we going to encode these using the Jordan-Wigner transform, which is very popular, partly because it's very easy to implement, something a little bit more sophisticated like Bravi-Kitaev, which is more efficient but less easy to implement, or even something more sophisticated like that, like BK Superfast. And then when we start doing our simulation, we have this occupation number basis, but how do we pick our very first initial ansatz? Do we pick something Hartree-Fock style? Or maybe post-Hartree-Fock, and which basics functions are we going to pick for that encoding? STO3G, which again is very popular because it's very accessible, but is in general not a particularly good representation of what we think the underlying molecule looks like, or something more sophisticated. So right from the get-go, when we're even encoding these chemical problems for the quantum computer, we have a huge amount of freedom to pick how we're going to try and represent the problem. And that representation choice can have a very large impact on the accuracy and feasibility of our simulation. And then we're going to apply these parameterized operators to our initial ansatz. So which ones? We have to also pick, first of all, is there a maximum number of electrons that are going to be allowed to interact with each other? Are we going to try and exclude some operators based on symmetry? For example, a common version of doing this is saying that you can't move out of a specific spin sector, or you try and say, like, the molecule has some underlying geometry, so I'll exclude any excitation that would violate that constraint. And then, having done all that, we also have to decide which molecules are we even going to try and study, for example, with classical simulation to validate our approach. The whole point of doing this is that we want to find a system where the quantum computer can outperform a classical system, and we also would like to eventually be able to share our results with people, so we need to be able to run the simulation in a reasonable time frame, which often constrains us to running small molecules, even though those are the easiest ones to get right, and not the molecules that we know are going to be challenging for the classical systems we're trying to beat. So it's very common today in the literature. I don't have a very nice survey like Nathan did, but just if you go and read a large number of papers about the variational quantum eigensolver for quantum chemistry, you'll see a lot of choices reoccurring. The Jordan-Wigner encoding, as I mentioned, is extremely popular, partly because it is easy to write down and because many libraries like PennyLane implement it out of the box. It's also quite easy to come up with an initial Hartree-Fock state using these STO3G orbitals. And it's a reasonable starting point, especially for the small molecules that are tractable to run today, although it's probably not something we should be super confident in scaling up to the really complex molecules we're interested in actually applying these devices for. And then again, for tractability reasons, and of course there are also sort of asymptotic arguments explaining this, we're only going to focus on smaller excitations that involve 1 or 2 electrons, partly, again, because you can make a lot of progress with this, and it's already challenging today, but it might be something that doesn't scale that well when you have hundreds of electrons in the system interacting with each other. Another very common popular choice today is to adaptively add the operators that you've chosen to your ansatz. This is called adapt VQE. And this is also partly done for scaling reasons. And then we also see, of course, that in the literature, most people are studying kind of the same library of very small molecules, like hydrogen change, lithium hydride, or beryllium hydride. And finally, again, to harken back to the great question we had at the end of the previous talk, many of the simulation results in this field are state vector exact simulations, which is great because that allows you to make progress and understand the feasibility of your algorithm. But we know that's not a real effective representation of what the device is going to do. So we've already made, in general, a lot of choices that kind of constrain how well our simulations represent, A, the molecules we want to study, and then B, the devices we hope to study them on. So if you'd like, we can draw up like a schematic representation of what we're doing here. We start off with, let's say, like an 8-qubit system, and you apply your initial Hartree-Fock state, which I've shown here in purple. Hopefully this renders okay, especially for the stream. And then we use some procedure to start applying excitation operators to it. So for example, here you can pick some operator that would move the state on the 0th qubit to the 5th qubit, which I've represented as Q4 there. And that has some parameter. Then you apply another operator with its own parameter. And through some operator picking procedure, which we'll go into in a little more depth, you can choose operators out of a pool and stack them onto your ansatz and hopefully end up with something that will drive you towards the ground state. And even in this procedure, there's a lot of freedom because you can constrain whether or not you're allowed to pick the same operator twice. And again, are you allowed to violate symmetry? Do you try to pick the operator with what you think is the biggest contribution, or operators that don't overlap that together will give a larger contribution than the one with the single greatest one? And there's no sort of theorem that tells you which one is the right answer. The only option you have, kind of similar to machine learning, is to just do it and try. And that requires doing a huge amount of classical simulation and probably writing a bunch of new code that perhaps most people don't have time to do. So I've iteratively built up my excitations to stack on top of my Hartree-Fock state. That's great. Now I have a reasonable guess for what my ansatz should be, and I can start optimizing all the parameters in this and hopefully end up at a reasonable representation of what the ground state is going to be. So easy. The problem with this is that performing this procedure on hardware that's going to be available in the near term is very, very difficult for a couple of different reasons. One big one is that the existing QPUs we have today have very low quantum volume, by which we mean that the amount of gates that they can execute is very limited, especially as the circuit gets deeper, without completely succumbing to noise. So in the little cartoon schematic I drew, you could probably see that the circuits that are generated in this VQE procedure tend to grow very deep pretty quickly. And there's lots of long-distance 2-qubit gates, which is generally a situation, especially for certain device architectures, that's unfriendly if you're running something in the absence of true fault tolerance. Another issue is that the qubit counts you need can grow very large very quickly, which again constrains the depth of the circuit you're able to execute without just completely succumbing to noise very fast. Then, when we're trying to pick the excitations to add to our circuit, naively, in the most commonly used ansatz, UCCSD, the number of possible operators we can apply grows as n to the 4, so where n is the number of qubits. And the Hamiltonian we're going to use for the chemical system that tells us, how good is this excitation, should I add it or not, and then when you're doing the optimization procedure, that also has n to the 4 terms. So the product of these two things is n to the 8. So the naive scaling of this is polynomial, but 8 is a pretty bad exponent to have in polynomial scaling. It's certainly better than 2 to the n, like for a naive, if you didn't know anything about chemistry and you just tried to simulate every electron in the system. But that doesn't mean it's necessarily going to be feasible, even in a, if you're classically simulating the VQE, let alone on real quantum hardware. So the question we'd like to ask ourselves is there a way we can try and attack this n to the 8 scaling, at least in its most unpleasant parts, and try and drive this stuff down and make it feasible to run either in simulations or real hardware in the near term while we wait for fault-tolerant systems to arise? And that's kind of going to be the focus of a lot of this talk. An additional problem is that the hardware we have today in general is slow and serial. So what I mean by that is if you were trying to run a classical simulation of all this, you could say, well, I'll use an HPC system, which is usually always available, and there's a lot of compute power that you can scale out to. But the quantum hardware, you can't just say, okay, well, I have one trapped ion device, so I'll just spin up 10 more of them and try and run everything in parallel. That's not possible to do. So you really have to be kind of judicious about how you run the final tests of your algorithm on the quantum hardware, which means you have to try and get a lot of insights, A, out of classical simulation, and B, you're very constrained in what you can actually test on the real device. And all of this is compounded by the fact that the devices we have today experience both shot noise and then errors because they're not fault tolerant. And even in the fault tolerant regime, the shot noise issue would still be present. So the upshot is that there's a lot of reason to be excited for using quantum computers to simulate quantum chemistry, but there's a lot of challenges that we're going to have to be honest about and try and overcome while we get there. So there's a lot of sort of hills to climb and valleys to try and get over to try and make this an actual feasible application of quantum computing. So specifically, when we say that the scaling is like n to the 4 for Hamiltonian, what do we mean by that? So these Hamiltonians for the chemical systems, as we showed in the cartoon earlier, are made up of what we might call polysentences, where they're a sum of linear combinations of poly operators, and each element in the sum has some poly weight associated with it. This might be an okay situation to be in if most of those summands had a coefficient that was really small, so they didn't contribute much. Then you could say, okay, well, I'll make an approximation and neglect them. And indeed, this is what, for folks coming from condensed matter or like theoretical chemistry people, have classical techniques that effectively do this, where you try and neglect sort of long distance contributions that don't affect the final outcome much. Okay. But in many of the encodings we deal with today, especially with the basis set choices we make, we're in a frustrating position where a lot of these words in the sentence all have high contribution weight. So you can't really neglect them without dramatically decreasing the fidelity of your final result to the actual system you're trying to simulate. And as we mentioned, the number of words in the Hamiltonian grows as the fourth power of the qubit count, which is pretty big, very fast. So for example, for something with like 12 qubits, you could very quickly have several thousand terms in H. And for something with 20 qubits, if you don't have some scheme to try and get rid of these, or try and at least reduce their number, you can soon have 20,000 terms in that Hamiltonian. And if we think, what's the shot throughput rate of a quantum device today? Like, if it's 10 to the minus 3, and you have 20,000 terms in the Hamiltonian, that's just not practical. The device is not up 24/7, so you're quickly going to be running into the fact that the device is recalibrated while you were trying to measure the Hamiltonian, and there's lots of problems with this. And when we're doing the parameter optimization procedure, we have to measure H multiple times, which is pretty frustrating because there's n to the 4 terms in it. And even if we're using an advanced optimization technique like SPSA, this still means a huge number of measurements at every single training iteration in the procedure. And the problem is even worse if we're using a naive technique to compute the gradient to either make the update or choose operators in the first place. That's where we really hit that end of the 8 scaling. And one might say, okay, well, then I'll just work on finding a better encoding of the underlying Hamiltonian to try and reduce these scaling factors or the qubit count I need, which is a great thing to do. Many people are working on this, but of course, it's not obvious that such a thing even exists. And if it does, it's not necessarily super easy to find. Such a thing may exist out there, but it may take you until fault-tolerant devices exist to come up with it. So what can we do in the near term while we're waiting for both these things to happen to try and make more progress with the tools that we have available with us today? Another way of phrasing this question is how can we extract the useful information from the Hamiltonian in a more effective way? So what we're trying to do is use some information we've encoded in our Hamiltonian to try and A, choose the appropriate operators, and B, make good updates to the parameters we have. So is there a way we can do that that at least doesn't hit this scaling as badly, but still lets us make reasonably good heuristic choices? So there's sort of 2 generic schemes we can apply to do this. These aren't the only 2, but they're 2 that I'm going to talk about today. One is to say, well, I don't want to deal with this Hamiltonian at all if it has such awful scaling, and I'm going to use some easier to measure statistics to pick operators from the excitation pool and apply them to my ansatz. And this is maybe a reasonable thing to do because often in VQE we say, okay, well, I'll compute the gradient of all the operator parameters with respect to H, and whichever operator has the biggest gradient is probably the one that will contribute most to finding the ground state. Now, there's no analytical result that promises that it has to be true. So effectively, what you're computing when you do that sort of step is a heuristic importance measure that you think is a pretty good guide to what the right operator to add is. But it's a heuristic, so maybe you can find a better heuristic. Or perhaps you could find a heuristic to that heuristic that still gives you most of the important information. The issue with this is even if you can pick the operators from the pool very effectively, you still need to do the optimization step, which is, in general, very expensive. So perhaps you'll still continue to use the Hamiltonian, but you'll try and find a way to approximate it. And perhaps one way to think of this is if you can try and find some sort of Hamiltonian-shaped object that still contains most of the essential physics of the Hamiltonian, but without all of the fine detail. Kind of similar to how in machine learning algorithms are often able to identify very JPEG compressed images that don't have a lot of the fine detail, but it's still identifiable to the machine learning algorithm and your eyeballs as a car-shaped thing. And that's enough to tell you and the machine learning algorithm, okay, that's a car and it's not a bicycle. So can we come up with something like this for quantum chemistry Hamiltonians? So there have been a couple techniques developed recently for trying these sorts of things. One option, this isn't, again, the only one, but it's one that we've worked on with our partners at Quantify, is selecting operators from the pool without computing the gradient. So this specifically allows us to avoid running that end of the 8 step to pick operators from the pool to apply to our ansatz. So what we're going to do is compute a heuristic to a heuristic, which is much easier to measure. And effectively, the way this works is this fast VQE algorithm computes only the diagonal components of the Hamiltonian, which it's able to do in one step rather than n to the 8. It's a pretty good scaling reduction. And the claim is this allows you to still capture the essential physics of the problem and select the best operator. If you're interested in reading this paper, it is on arXiv. You can use this QR code if you'd like. And what's nice about this is it's all of these expectation values that are used to compute this heuristic are simultaneously measurable, even in the shots greater than 0 context. And they're able to use classical resources, which of course are cheaper and much more available to do the necessary preparations for this step. And so this allows them to dramatically decrease the scaling for the operator selection, which is great. And this technique is not yet available in PennyLane, but perhaps some enterprising hacker might be interested in trying to apply it. So if you're interested in seeing what the actual results look like, this is from their recent paper and then blog post that they've published in concert with us on the Amazon Bracket team. Again, these are folks from our partners at Quantify, which is a Danish company. So what they've done is they run both classical simulation and then on real hardware, the operator selection step for this adapt VQE algorithm. So they run this fast VQE technique for choosing operators out of the pool on, I think, our simulator, a noise simulator, and then on Rigetti. And then based on those results, they pick the operator and then do the optimization step on a state vector simulator. So the goal here is to kind of show that the operator selection step, at least, you are able to capture the essential information to pick good operators, even in the absence of computing the full n to the 8 scaling gradient, which is very important. And what's also rather interesting about this is they found that the presence of noise, at least on the Rigetti device and then the noise simulator, actually often helps them make good operator choices early, perhaps because it gets them out of some bad minimum or something. This is obviously something that I think would be interesting to understand better. So they're able to do a much sort of quicker simulation of choosing these components of the ansatz, but this doesn't yet address the issue of doing the parameter optimization step, which is still a really big barrier for VQE. So the rest of our focus here is going to be looking at various means of approximating the Hamiltonian. So this object, the expectation value of h given our ansatz, is kind of the essential chunk we need for doing these optimizations. This is effectively computing the forward pass for the optimization if you're coming from a more machine learning background. And we're going to talk about several techniques that have been used to try and do this. And as an analogy, kind of what we're looking to do here is we take several pictures taken with a color filter, and then we use that to reconstruct the full color image. This is like from the early history of color photography. What you would do is you would put like a red, a green, and a blue filter over your camera and take several black and white images, and then reproject with the color filters to try and come up with the full color image. So these images are from the early 20th century. And as you can see, the reconstruction isn't perfect, but it was definitely a very important early step in the development of color film and color photography. And so our goal here is to kind of come up with something analogous for the process of approximating the Hamiltonian's expectation value and hopefully sort of drive the evolution of this whole field in the same way that these early experiments in taking colored pictures did so for the film and photography industry. Okay. So the first technique we're going to talk about is classical shadows tomography. In this sort of a procedure, we take some number t snapshots of each qubit in a basis where each qubit is measured with respect to some operator randomly chosen from the 3 set of polys. And from there, we're able to reconstruct a density matrix for the teeth snapshot using a result projector. And the claim is that we can reconstruct the expectation value of the Hamiltonian by averaging over these snapshot density matrices. So you can clearly see that obviously the effectiveness of doing this, unless you guess very lucky the first time, is going to depend on the number of snapshots you take. And this isn't necessarily a free lunch claim that you'll be able to take like some very minimal number of snapshots and perfectly reconstruct the Hamiltonian. Rather, you need to kind of empirically determine what the appropriate T is for your given situation. And you can imagine, for example, taking one snapshot, checking the variance, and continuing that, and sort of asymptotically approaching what you think is a reasonable estimate for this expectation value. So this technique is already implemented in PennyLane. In the VQE context, I have my little pseudocode here. And there's also some really nice demos that are available on the PennyLane website that you can check out if you're interested in this. So all you need to do is build up your ansatz where you start with your Hartree-Fock state. You apply your previously selected excitations and then your new excitation. And finally, you compute the expectation value of H using the shadow xval technique. And the number of snapshots you'll take is determined by the number of shots you pass to the device. So this is really easy to set up in PennyLane, which is awesome. And you can use this to kind of experiment with how well this technique works for either like your gradient computation, if you'd like, or choosing the operator or doing the optimization step. Another technique that is also available in PennyLane, which is awesome, is trying to group the Hamiltonian into what are called qubit-wise commuting polys. Oh. So the way this works is that we said we had like n to the 4 of these Pauli strings or Pauli words, and we'd like to find groups of them that can be measured simultaneously. So if, for example, we have a Pauli that's Z's on qubits 1 to 5 and X's on qubits 6 to 10, those are simultaneously measurable because they don't contain any polys on the same qubit that are not simultaneously measurable. So using algorithms from graph theory that are designed for what's called click finding, you can reduce the total number of measurements you need to make to exactly compute the expectation value of H by a very large amount. Up to 90% in some cases. So that's great. The issue, of course, is that if the total scaling of the number of terms is n to the 4, where n is the number of qubits, let's say if n is 10, that means there might be 10,000 elements in H. So reducing it by 90% is awesome, but it still means there's 1,000 terms in this you have to measure, which can be quite a lot. And so the number of non-commuting groups will still grow quite quickly if you're using this qubit-wise polyword strategy, even though the reduction you see is obviously very helpful. And again, this is very easy to implement in PennyLane. There's great support already for computing what's called the grouping of a Hamiltonian. You generate some Hamiltonian, let's say, and then you can just apply this QWC or qubit-wise commuting grouping to it. And then you can simply measure the expectation value as you normally would, where in fact, what PennyLane does internally is it will compute the separate 1,000 expectation values for each commuting group and then combine them at the end to give you the result. And that happens behind the scenes, and it's pretty nice and convenient. So then one might ask, these two techniques seem great. You're able to reduce the number of shots you need, and you're able to use a lot fewer sort of groups in general. Can these be combined? So recently, as in the last year, there's been some work on using so-called shadow-informed grouping, or in this case, I've called it colorful shadows. And this is kind of analogous to the color photography example I showed in the beginning of this section, where what we'd like to do is combine grouping with classical shadows. And the idea here is that you can prove actually that this is able to measure these so-called polywords or phrases very effectively. Again, this technique is also not implemented in PennyLane yet, but perhaps an enterprising hacker might be interested in trying this. And if you're interested in reading the paper, again, it's available at this QR code. So in this situation, we've got 6 poly phrases on 4 qubits, and I'll explain what the colors are. So these coefficients here are in ascending order. So this poly phrase at the top has the highest weight, and then C2 here has lower weight, and I probably should not have the microphone next to the speaker. That's a little dicey. Oh, shoot.
Yeah, you gotta stand away from the projectile.
Sorry. Okay, there it is. It's back. All right, lesson learned. C4 has lower weight than C3, and C5 lower, and C6 lower. Okay. And then as we move right in the table, those are the 4 qubits. So an empty box means it's just the identity. Green is one of the polys purple is another, and pink is the third. It's not particularly important which one each one is. It's just they're 3 distinct polys. So if I give you some poly chunk like this, or like a poly phrase, can you find an efficient shadow scheme to approximate this thing? And if so, how do you do it? So the paper argues effectively what you should do is you compute an overall weight for each option on each qubit, and they give a scheme for doing this in the paper, which I won't go through here, but you're welcome to read it. And then you descend in decreasing level of weight through this poly phrase and allocate which measurement you're going to make on each qubit. So in this case, the top line has the highest weight, so we'll pick whatever the green poly is on qubit 2 and the purple one on qubit 3. Or sorry, qubit 1 and qubit 3. Then we go down the next one in the table, and we see that on qubit 3, everything's fine. There's just an identity, so we'll measure that one again. And then on qubit 1, there's a conflict. We could stick with the green, or we could go with the pink. But our weight formula says that the green one has higher weight, so we should go with that. So we're choosing here to make an approximation where we say green and pink are not simultaneously measurable, but the contribution of green is more important, so I'll approximate with that. Then at the next level, we stick with green again because there's just some identities. We add a new purple in because we encountered one of those on qubit 2 in this sort of third row. We keep proceeding. We hit another green. That's great. So if we'd encountered another pink here, we would need to see now if the total weight of the pinks from 2 and 4 overwhelmed the weight from 1, but luckily we didn't encounter that situation. If you do, there's a formula for figuring out which one to pick. But effectively, what you'd like to do is bias towards the one with the highest contribution to the overall phrase sum. Then we keep advancing down the list of qubits. So we see now there's a pink one on qubit 0, and there's still green on 1, purple on 2 and 3, and then finally, in the last row, we hit another pink, but I've kind of cheated here and said again that the pink is lower weight, and it's low enough that the weight of the greens overwhelms it. So now we have a scheme for measuring on all 4 qubits, some final measurement protocol. So we compute the expectation value with respect to this, and we use that to approximate the weight of all of the summands in this chunk. And this paper, again, gives like a more developed scheme for how you pick these phrases and then how you just make the sort of decision from weight to weight. But this is a provably more effective way of combining both the qubit-wise commuting scheme and then also the classical shadows technique in kind of a group-aware way. And so the goal here is to allow us to approximate these Hamiltonian expectation values more efficiently. Cool. And then the last technique I'll talk about, which I didn't make any attractive tables for, which I'm sorry for, is using positive operator valued measurements to do tomography similar to classical shadows. So this technique is a little different because the previous two we looked at, both the qubit-wise commuting and the shadows, have us using exactly the number of qubits we started out with that we were given. This technique is a bit different, where what we say instead is we'll add a new qubit array of ancillas, and we'll pair each ancilla with the one original measurement qubit in my original VQE problem. So effectively, we've doubled the number of qubits we need, but that might be worth it if we can effectively simulate the Hamiltonian thanks to doing this. So the way this scheme works is we construct a positive operator valued measurement. And again, if you're not familiar with that, totally fine. Check out the paper link here, which involves entangling each of the measurement qubits with an ancilla through a unitary U, which is a linear combination of 2 qubit polys. And this instantly generates for us 8 trainable free parameters for each measurement qubit. And our goal is to adaptively tune the number of shots and the number of parameters, and the parameter values to approximate H for whatever initial wave function we put in. So for each qubit, we've got these 8 trainable free real parameters, and we go shot by shot, making updates to them using whatever update scheme you want to use. And then when we end up with the trained free real parameters that we think give us a good approximation of the Hamiltonian, we're able to use those to much more efficiently measure the final state as we perform the VQE procedure. And we can also compute easily the variance of the expectation value of age that tells us, I've added enough operators to my VQE ansatz that is drifted from the initial one I used to train these parameters. So I need to do some update parameters to my Hamiltonian approximation scheme and then restart the VQE procedure. And the claim here is that doing this allows us to use fewer shots total dramatically than doing something like qubit-wise commuting or naive classical shadows. So effectively what we're trading off here is having more qubits that we need to simulate or more qubits that we need in the real device, but we're going to be able to get away with far fewer shots. So if you have those more qubits available, that's awesome. If not, you may need to try and figure out some other way to approach this issue. So finally, I'm going to talk about an ongoing project that I'm working on at my work at Bracket, which unfortunately I don't have a lot of data to show yet, but it's kind of ongoing in the spirit of seeing which of these techniques is most effective in which situation. Like I've outlined a whole library of techniques, which is awesome, but which one is good? Like which should you use when? If you use these, will your thing still not be feasible to run on a quantum computer or not? How would you know? So our goal is to do a bunch of classical benchmarking using various techniques to try and make things most favorable to what the actual quantum computer would do, and see which of these techniques is most viable in which situation, which should you use with certain molecules and with certain encodings. So we're studying this using this Tetris Adapt VQE, which is an update of naive Adapt VQE to try and generate shallower circuits. And we're studying, just for now, even the simple molecules I outlined earlier, the hydrogen chains, lithium hydride, beryllium hydride, partly because it's kind of similar for anyone with a condensed matter background. If you can't get the Ising model right, you're not going to get anything else right. And if you can't get MNIST in image classification, you're probably not going to get any more complicated problem. So if you can't handle these molecules to some degree of accuracy, you're probably sunk for more complicated systems like benzene or CO2 or anything with a more complicated metallic atom in it. And we're also interested in running this both at finite shots and with and without kind of realistic or device-inspired noise. Again, because what we would like to do is generate some guidance of like when will this be useful on a real device, or what properties would the device need to have for this to be feasible to run on it. And we're also looking at various techniques for doing the optimization and gradient selection, for example, using SPSA. How much of a benefit does it give you over parameter shift, or is the accuracy loss too bad? Looking at things like the different encodings I talked about, things like the Brodby-Kitaev encoding can allow you to use fewer qubits. Is that enough to make some of these approximation techniques more or less feasible? And finally, of course, we would eventually like to run some of this on real hardware, which is kind of the real acid test of this. You can do 1 million simulations, of course, but the real test is whether your technique succeeds on real hardware. So effectively, what we would like to do is generate kind of like a recipe book or a charge table for these kind of VQEs. Are they feasible? In what cases? What techniques do you need to use? Or what parameters do the devices need to achieve for this to be feasible in the NISQ era? So some open questions for this problem is whether you're going to be able to get away with using things like error mitigation, or are we really going to need fault tolerance? Are we going to be able to do any of this in the NISQ era, or do we just have to wait for real error-corrected devices? And how much does any of this extend to larger molecules? Part of the problem, of course, of focusing mostly on smaller molecules is that the very fact that they're easy to simulate can bias you in which technique you choose. Again, similar to the Ising model, where you have to get these right to have confidence in your technique, but getting them right, of course, doesn't mean it generalizes to systems with more complicated interactions. And then we're also interested, as I mentioned, in looking at these sort of hyperparameter algorithm choices of like, what's the best way to compute our gradients, to do our optimizations, which hyperparameters should we choose for the optimizer? Can we account for things like the real-world drift in the devices, when they go down overnight? Accounting for things like the actual chip topology when we choose the operators we want to include in our ansatz. Lots of other choices we can make. And then also looking at some of these new importance measures that aren't based on gradients. So one thing you might have noticed in this whole talk is that VQE, of course, like many people say, it's one of the more promising algorithms for near-term quantum computation, but it's such a huge family of techniques with so many possible hyperparameter choices or algorithm choices that we really need more clarity and more confidence about recommendations of what specifically to do. Because there's so many varieties of VQE, you could spend the rest of your life benchmarking it, which might be like an entertaining way to spend your time while you wait for fault-tolerant devices, if you like doing HPC workloads. But if you want to run something on real quantum hardware in the relatively near term, you need to quickly develop some kind of opinion about these various questions. So that's part of what I'm hoping to do with these simulations. And so kind of to sum up this segment of the talk, we'd like to stock our toolbox with effective tools for what we want to do. So we don't want to be doing the equivalent of like trying to hammer nails with the back of a screwdriver. That's silly. And similarly, we don't want to be using the wrong algorithm or approximation technique for the system we're trying to study. And we don't have a lot of clarity necessarily about the best tools to use. It's kind of a similar situation to Nathan's great talk about the ML algorithms, where there's a lot of like published materials about various techniques, but there hasn't been a lot of cross-comparison between them, partly because a lot of people, it's very hard to get other people's code to run. There's not a lot of incentive to do that comparison necessarily if you're trying to publish things. But this is something we really need to do to understand what these devices are going to be useful for and when. And this is a great opportunity for things like PennyLane that can help us with coming up quickly with tests for things like HPC simulations. And so finally, what we're going to talk about is how PennyLane and then the code I work on in Bracket can make it easy to set up these kind of simulations, run them, and transition to running on real quantum devices. So as I said on the title slide, I am an applied scientist at Amazon Bracket. We're one of the sponsors for QHack 2024. You can see us with the AWS logo right there. We're also providing credits and power-ups for the sort of longer-term hackathon, so stay tuned for that. So if you've never heard of Amazon Bracket before, I'll give a quick intro. It's our quantum computing service at AWS. It's fully managed, and it lets everybody from scientists to newcomers to the field to explore quantum computing. So you can build circuits or experiments using our SDK or third-party integrations like PennyLane. You can test it with simulators that we provide on our service, and then you're able to run on real quantum hardware using the same scripts you used in the build and test stages. And finally, you're able to analyze your results using a bunch of the convenience features that we offer. And so using PennyLane with Bracket is really, at least for me, very useful because I'm able to start with the pre-built templates and data sets for quantum chemistry that the PennyLane folks have worked really hard to build. Of course, they have many templates and data sets for other things, but since I'm working on chemistry right now, these are the ones I'm focused on. And using the integration with Bracket, you can go very quickly from a high-performance simulation to running on a quantum device. And it's now even easier to do this now that we've launched a remote decorator feature that allows you to take your script that you tested out in a notebook and run as a high-powered experiment or simulation using our hybrid jobs feature. You'll hear more about that during some of the later Bracket presentations. And you can use PennyLane's awesome high-performance simulators in jobs as embedded simulators or get priority access to the QPU when you use a job. And at QHack, as I mentioned, we'll be hosting office hours on Discord, so whether you're in person or remote, check us out there. And we'll also be providing power-ups during the hackathon at various stages, which again, you're gonna hear more about. Probably of interest to many of you is that we do provide access to various quantum computers. So here are the 4 QHPs that are available on Bracket right now. And in particular, I just want to call out for hackathon participants, especially if you get credits, OQC, Oxford Quantum Circuit's Lucy device is going to have extended availability. And we also are offering QEra's device, their analog Hamiltonian simulator, Aquila, during the hackathon. So if you're interested in using either of these real quantum devices, either come talk to me after the talk or any of the Bracket people who will be on the Discord. And finally, in the interest of not going too long over time, I'll just say thanks to everybody who's attended. Thank you to Xanadu again for organizing this awesome event year after year. If you're interested in using Bracket or using any of our devices during the hackathon, come to the Bracket workshop on Friday the 16th, and the PennyLane demo with Bracket also on Friday the 16th with my coworkers. And if you want to learn more about Bracket in general, feel free to grab any of these QR codes. And with that, thanks again, and I think we're good for questions.
Yeah, awesome. Thanks, Katie. Yeah, Guillermo, we can get to some questions. One thing that I noticed in your talk, this is super, super random, but I'm a condensed matter person. You pronounced Ising correctly. I never do that. It's easing. Fun fact. Yeah, Guillermo, anybody who wants to ask Katie a question, feel free to do so. We'll hand a mic over to you. Yeah, question in the front there.
Hi, Katharine. Thanks for the nice talk. In the first half of your talk, you spoke about reducing the measurement overhead. I have a slightly different question on that note. So, actually two. One, when you showed us the results from your quantum computer, what was the fidelity of your gates? And two, have you analyzed what actually happens, like when with the noisy gates? Like, how does the error scale with the probability of noise in quantum gates? And supposing supposing no spam errors, then what happens?
Yeah, so it's a great question. I think you're speaking about the data from Quantify, so let me just go back and pull this up. This is kind of a hybrid run that they did where they do the selection step with the quantum computer, but the actual optimization, which is the one that's in some effect like most vulnerable to noise, is done on the simulator. So they prepare, they have their ansatz that they prepare and then run on the quantum computer for the selection step. And they discuss in their paper how they exactly construct this. But then for the optimization, since it is pure state vector, the issue that you bring up of like the compounding noise is somewhat less relevant. It is during the operator selection step because the ansatz grows at each step, so the circuit you're running becomes deeper. And then to the question about 2-qubit fidelities, so as you can see here, they ran this on Rigetti's Aspen M3. Off the top of my head, I don't remember exactly what the mean 2Q was, but I think we do have that data historically. You could look it up. Having not run on Aspen M3 myself super recently, I don't want to like say anything too specific about the device's performance, when they ran this. But my understanding too is that because Rigetti's device is superconducting, the 2-qubit fidelities can vary like quite a bit between the different Qs. So I think that they were using the whatever tooling Rigetti provides to come up with like the most efficient mapping. But since I didn't run these simulations myself, I don't want to say anything too strong about what they did or didn't do. But I think they do include a lot more details of how they actually ran this in their paper, which is available this QR code. Yeah.
One quick question. So, in this graph, was any error mitigation used?
I don't think so.
Okay.
Yeah.
Okay, any more questions for Katie in the audience here? Okay, if not, we have one question in the chat from Andresu Lead. I think this person's been at QHack before, actually, so welcome back.
Welcome back, yeah.
Yeah, so maybe a bit more broad, but among the methods you've mentioned, which there were quite a few, which has proven to be more effective, or do each of them possess distinct advantages and disadvantages?
Yeah, it is a good question. I mean, to answer the first point, which is most effective, that's exactly what our benchmarking project hopes to find out. Or maybe a better way to say it, I think, is like which is most effective in which situation. One, of course, you can't rule out the possibility that one just blows all the others out of the water, but I strongly suspect it's going to be one of these, like in this situation, you should do this, and in this other one, you should do this other thing. And then, yeah, I think that each one kind of does sort of have advantages and disadvantages. For example, with some of these like POVM schemes, you do need double the number of qubits for this ancilla entanglement procedure, which is great if you have that many qubits. But if you don't, it really limits the size of problem you can simulate, or you have to constrain the number of electrons you want to run with, which might affect the accuracy of your results. And then for some of the others, like and this is also in some ways true of like some of these adaptive shadow techniques or like the adaptive POVM techniques, you have to sort of like run shot after shot after shot, hoping you converge, and hoping that the variance of your expectation value goes down, but you're not necessarily given a guarantee of when that happens, and it could take a very long time. So you aren't necessarily able to say like with confidence going in, like I know how many shots I'm going to need to be able to converge this. Versus with some of the qubit-wise commuting techniques, you can say, once I've partitioned this into the groups, I'm comfortable just running like a certain number of shots for each one, so I'm guaranteed that I'll use maximum this many, and I will be able to finish the run by the time the device goes down, for example. And then in the shadow grouping technique that I talked about with the my colors that I spent some time drawing. One advantage of this, I didn't pull out the entire proof, but they do have upper bound on the error that's induced by doing this versus just using straight up qubit-wise commuting, which it's always helpful if you have like an actual proof that the error is maximum some number. Then at least you can kind of account for that in the rest of the simulation by, for example, running more shots or making your phrases smaller, things like that. So at least then you're aware kind of what you're trading off in each scenario. So, yeah.
All right. Any more questions for Katie in the audience here? No? All good? Okay, well, one more round of applause for Katie. Thanks so much for joining us again at QHack. Yeah, thanks so much for joining us again, Katie. Really appreciate you being here. Are you here for most of the day?
Oh, sorry. Yeah, I'm here today and tomorrow, so yeah.
Cool. All right. So I guess if anybody has any questions in person, feel free to find Katie and ask her some. All right. So we have a panel in the afternoon that's going to be live streamed. That's a new addition to the QHack agenda, I suppose. We're going to talk about employment in this industry. So we have some really cool people on this panel. Anastasia Marchenkova is going to join us. She's a big influencer on YouTube and Twitter and stuff, among other things. So that'll be awesome. Roger Luo, he's a previous colleague of mine. He's I think he's here actually. I saw him walk in. Roger is one of the best quantum programmers that I know. And then we have Richard Given, who's from Haiku. And Jake Malarios from CDL. So yeah, definitely come back for that. For those of you online, we're going to take a couple hours here for a break. But definitely come back. Thanks again to our speakers, and we'll see you at 2 o'clock back in the kitchen. Cheers.